morning, students. In this video lecture, I'll discuss about Raoult's law, ideal solutions, non-ideal solutions, and azeotropics mixtures. First is Raoult's law. Raoult's law, students, is the quantitative relationship between partial vapor pressure and the mole fraction of a volatile component. According to Raoult's law, partial vapor pressure of a volatile component is directly proportional to its mole fraction in the solution. Consider a solution AB where A is solvent and B is solute. Both A and B are volatile. According to Raoult's law, partial vapor pressure of component A, that is PA, is directly proportional to its mole fraction XA, or PA is equal to PA naught XA, where PA naught is vapor pressure of pure component. PA naught is partial vapor pressure of component A, and XA is its mole fraction. Similarly, PB is equal to PB naught XB. This is according to Raoult's law, and we know according to Dalton's law of partial pressures. Remember, according to Dalton's law, vapor pressure of solution is the sum of partial pressures of all the components. That is, P is equal to PA plus PB. Substitute the values of PA and PB. P is equal to PA naught XA plus PB naught XB. Graphically, Raoult's law can be expressed here. See, on this axis, on x-axis consider mole fraction, on y-axis consider vapor pressure. This side, let mole fraction of component A is 1, XA is equal to 0. Similarly, mole fraction of component B on this point is 0. It keep on increasing from left to right. XB is 1. Means on two extreme sides, pure components A as well as pure component B are present. According to Raoult's law, as the concentration of component B keep on increasing, so as its vapor pressure. This one. Similarly, it's true for component A also. First line represents partial vapor pressure of component A, PA, which is equal to PA naught XA. Another line represents partial vapor pressure of component, first one is partial vapor pressure of component B. This line represents partial vapor pressure of component A, PA, which is equal to PA naught XA. For representation of vapor pressure of solution, join these two lines. This is the vapor pressure of solution. P, which is equal to P A naught XA plus PB naught XB. This point represents vapor pressure of component A, which is represented by P A naught. And this point represents vapor pressure of component B, which can be represented as PB naught. Okay, students, one more time, revision. Raoult's law is the mathematical expression which relates partial vapor pressure of a volatile component to its mole fraction in the solution. And the total pressure of all the volatile components in the solution can be represented by Dalton's law, which is equal to P is equal to PA plus PB. This is the Raoult's law for a solution which contains two volatile components. Second one is Raoult's law for a solution of non-volatile, remember this, non-volatile solute. If a solute is non-volatile, then vapor pressure of component B becomes 0. Reason, since component B is non-volatile. Then vapor pressure of the solution is equal to vapor pressure of component A only. Again, vapor pressure of solution is equal to vapor pressure of component A. You can say A as solvent only. Or P is equal to PA naught XA. Again, a solution which contains a non-volatile solute, for that kind of solution, its vapor pressure is equal to partial pressure of component A only. That is, P is equal to PA naught XA. Graphically, this line is non-existent. So vapor pressure of solution is only because of its volatile component, and that is A. These are the two statements of Raoult's law. First one is Raoult's law for solution containing two volatile components. Second, volatile liquid and a non-volatile solute. Next topic of the day, students, is ideal solutions. Ideal solutions are those solutions which obey Raoult's law over entire range of concentration. Those solutions which obey Raoult's law over entire range of concentration are known as ideal solutions. For ideal solutions, there are some important points to remember. First, solvent-solute interactions, that is AB. The interactions which are set up when molecules of solvent interacts with molecules of solute. AB interactions. Imagine कर पा रहे हो, A are the molecules of component A that are solvent, B are the molecules of solute. A-B interactions in ideal solutions are equal to A-A interactions, solvent-solvent interactions, which are equal to solute interactions. Means all three kinds of interactions, A-B, A-A and B-B, all three are equal. Second point, enthalpy of mixing is 0. That means no heat is required or evolved when solvent and solute are mixed together. That is, reaction is neither exothermic nor it is endothermic. Delta H mixing 0. Third, there is no change in volume when solvent and solute are mixed. That is, if we mix 50 ml of A with 20 ml of B, expected is 70 ml of AB. Exactly, we will get 70 ml. It can neither be 69 ml or 71 ml. So delta V mixing is 0. So these are the 3 points you must remember. All interactions are equal. Delta H mixing 0, delta V mixing 0. Fourth is example. Examples of ideal solutions are solution of N-hexane and N-heptane, solution of benzene and toluene. Basically, those components form ideal solutions which are of comparative molecular mass, comparable structure and properties. These are ideal solutions. Next is students, non-ideal solutions. Those solutions which does not obey Raoult's law over entire range of concentration are known as non-ideal solutions. So in non-ideal solutions, the interactions among solvent and solute are not equal to interactions among solvent molecules and also not equal to interactions among solute molecules. Second point, delta H mixing enthalpy is not 0. Means reaction of mixing is either exothermic or endothermic. Third, delta V mixing is not 0. So in case of non-ideal solutions, 50 plus 20 ml is not 70. It will be less than 70, or in certain case it may be more than 70 but not 70 ml. On the basis of interactions among solvent and solute particles, non-ideal solutions are categorized in 2 ways. Non-ideal solutions. Non-ideal solutions are of 2 types. showing positive deviation or negative deviations from the Raoult's law. So non-ideal solutions are of two types. Solution which shows positive deviation and a solution which shows negative deviations from the Raoult's law. First, we'll take up these type solutions which shows positive deviations from the Raoult's law. These are the solutions in which solvent-solute interactions are less than solvent-solvent interactions and also less than solute-solute interactions. That is, when solvent and solute particles are mixed. Obviously, the third type of solutions are set up which are AB interactions which are weaker as comparative to original interactions which are present among solvent-solvent molecules or solute-solute molecules. Second, delta H mixing is greater than 0. Means reaction is endothermic. It means energy is required to keep solvent and solute particles inside the solution. Reaction is endothermic. Third is delta V mixing is greater than 0. It means if we take 50 ml of A and 20 ml of B, then we'll get 72 ml of A, B. Since the interactions among solvent and solute particles are weaker as comparative to solvent-solvent or solute-solute particles, then these particles tend to escape from the solutions. Intermolecular interactions become weak, which results in increase in volume. So delta V mixing is greater than 0. In negative deviations, opposite is true. Solvent-solute interactions greater than solvent-solvent interactions, also greater than solute-solute interactions. Delta H mixing is less than 0. That is, reaction is exothermic. Third, delta V mixing is less than 0. So it means 50 plus 20 is less than 70. Fourth is graphical representation. Graphical representation of solution showing positive deviations and negative deviations from the Raoult's law. This x-axis represents mole fraction, vapor pressure, vapor pressure. Vapor pressure of component A, it will be vapor pressure of component B. In ideal case, these dotted lines represents an ideal solution. But for a solution which shows positive deviations, since vapor pressure becomes more as expected from the Raoult's law because of decreased interactions, so we get a curve like this. This line represents partial pressure of component B. Let me mark this. This is XA1, XB0, XA0, XB1. So as mole fraction of component B increases from 0 to 1, its vapor pressure increases and becomes maximum at this point, PB naught. So partial vapor pressure of component B is this, which is greater than PB naught XB. PB has to equal to PB naught XB according to Raoult's law, but it is greater than in case of positive deviation. Similarly, for component A, PA, partial vapor pressure of component A is greater than PA naught XA. And vapor pressure of solution P is greater than PA naught XA plus PB naught XB. Similarly, for a solution which shows negative deviations from the Raoult's law, graph can be plotted like this: XA1, XB, 0, XA, 0, XB1. This line represents vapor pressure, this point, maximum vapor pressure of component B, vapor pressure of component A, PA naught. For ideal case, it should be like this. For a solution which shows negative deviations means there are more interactions among solvent and solute particles as comparative to solvent-solvent or solute-solute particles. Therefore, the vapor pressure is less than expected from the Raoult's law. So curve is bit downwards. This represents partial vapor pressure of component B, which is less than PB naught XB. This represents partial vapor pressure of component A, which is less than PA naught XA. This line represents total vapor pressure of solution, which is less than PA naught XA plus PB naught XB. Last point in this topic is example. Example of solutions which show positive deviations from the Raoult's law is solution of water and ethanol. And the example of solution which shows negative deviations from the Raoult's law is a solution of water and nitric acid. Another example, this is solution of chloroform and acetone. This is chloroform. This one is acetone. That is enough about Raoult's law, ideal solutions and non-ideal solutions. Thank you. Students, next topic of the day is azeotropes. Azeotropes are those solutions which can distill unchanged in composition, that is, which behave as a pure component. Azeotropes term is derived from a Greek word azeotrope, which means boiling without change. Now, azeotropic solutions are of two types: minimum boiling azeotropes or maximum boiling azeotropes. Minimum boiling azeotropes are the solutions which shows positive deviations from the Raoult's law. This we have already discussed in detail earlier. Now, what this minimum boiling means? Suppose we have a solvent A and a solute B. Solvent has boiling temperature 373 Kelvin. Solute has a boiling temperature of, let it be, 380 Kelvin. Minimum boiling azeotropes are those which boil at a temperature which will be less than 380 Kelvin, less than 370 Kelvin even. So boiling point of this solution AB will be less than 373 Kelvin. Got it? Again, what are minimum boiling azeotropes? These are the solutions which shows positive deviations from the Raoult's law. That is, there are less interactions among solute and solvent molecules. Intermolecular distances are more, interactions are less, so boiling point decreases below the boiling point of minimum boiling component. On the other hand, maximum boiling azeotropes. These are the solutions which shows negative deviations from the Raoult's law. Suppose we have solvent A with boiling point of 373 Kelvin, solute B with boiling point of 380 Kelvin. Solvent and solute are mixed to form a solution AB. If it happens to be an azeotropic solution, then its boiling point will be more than 373 Kelvin. It will be more than 380 Kelvin. So boiling point of solution AB will be more than the boiling point of maximum boiling component. Therefore, referred as maximum boiling azeotropes. Okay. Some examples. Example of this minimum boiling azeotrope is N-propanol, that is C3H7OH, and water. Example of next one is chloroform and acetal.